large protein, intracellular protein called a G protein, which then dissociates and sends out various signals. So schematically, this is what happens. This is the opioid receptor. Much of it is in the brain, but also in other parts of the CNS and the gastrointestinal tract. So this is morphine, binds to the opioid receptor. It binds in an appropriate way. It changes the shape of that receptor and results in in signal transduction. You get pain relief, which is what you want, but you get a lot of side effects from opioid receptor activation. Dependence, addiction, constipation, tolerance, nausea, and life-threatening side effects, respiratory depression, such as skilled prints, and poor cardiovascular function. Now, it was basically always thought that any drug that activated the receptor is like an on-off switch. You're going to get all of these together or none of those together. And it was just what you would get. So all opioids would have some blend of safe and unsafe aspects. But just really over the past 10 years or so, we've found out that the opioid receptor, and really all G-protein coupled receptors, are not simply an on-off switch. There are many different signaling cascades that occur after a compound binds to the mu receptor. There are G-protein dependent pathways and G-protein independent pathways. And moreover, not all drugs activate these pathways to similar extents. So this idea that you could have different signaling pathways and drugs could have different combinations of effects based upon this distinction has been the focus of Laura Bond's group at Scripps, Florida, my collaborator, an outstanding biochemist and molecular pharmacologist. She developed a strain of mice that is incapable of manufacturing that beta-arrestin protein, so that it's involved in a lot of the non-G protein dependent signaling. These mice were sensitive to opioid pain relievers, that is, they show pain relief effects that were normal in most other aspects, but their response to the opioids were different. They developed less tolerance. That means you didn't require a higher and higher dose to get the same analgesia, experienced less constipation, and most importantly, and most notably, they didn't appear to be in respiratory distress, even on overdoses of morphine or fentanyl. So Laura and others have developed this sort of two-path model. I showed it's really more complex than that. But you can consider a G-protein coupled receptor here capable of undergoing G-protein dependent signaling and beta-arrestin derived signaling. A biased agonist is capable of influencing the shape of the receptor in such a way that it might activate, say, the pain relief pathway over the beta-arrestin or the side effect pathway to some extent. So the mu receptor